welcome you all in this lecture on design of a legged robot. We have been seeing the many examples of design of a mechatronic system over last few lectures. This is the last lecture in that series, where I am going to discuss with you the various steps involved in the design of legged robot, which was carried out in our lab. Legged robots are very useful for the uneven terrain, okay, because these legs foot can be placed in a small area, okay. So they are suitable for uneven terrain. Okay. And here I am going to talk about the development of the compliant legged, the quadruped robot. Okay. The two links of the robot, that is this is what I am going to talk about today. Okay. So the bottommost the bottom link is actually the compliant one, which we have considered over here, and the body and the upper link are rigid one. Okay. And electrical actuators are used for actuation of each joints. We have seen already a lot of detail about the actual electrical actuators, and here Amble gate is demonstrated on the developed robot. Okay. Amble gate is one, you see that they have got the 4 legs basically. Okay. So one leg is in contact of the ground, one leg is in the air, whereas the 3 legs are in the contact at the ground. That is what we call as the Amble gate. Okay. And this developed robot can be used for testing various research aspects such as reconfiguration, fault tolerant control, posture control pertaining to the 4-legged robots. Okay. So here basically what objective of our development has been to that the robot should be able to walk with different static and dynamic gait pattern. Why I am taking this example over here, that after doing after learning all the various mechatronics components, actuators, sensors, okay, then microcontrollers, okay, digital control, analog control, all these aspects, the ultimate aim of any mechatronic system design is to the development of a mechatronic product. Okay. And this legged robot is very good example of that mechatronic product. Okay. So at the initial stage, it is difficult to decide the physical specification, and as you know that the design of any component is an iterative process. Okay. So you have to begin from somewhere. All right. So the design process started from the commercially available component size basically. Okay. And as the robot is compliant legged, let us start from the commercially available compliant link. Now compliant link, it is observed that why we took compliant link, because it is observed that the human and animal legs have spring like behavior. Okay. And generally mechanical springs are introduced to introduce compliance in the structure of a robot. Okay. And why we go for the compliance, because this compliance actually the improves locomotion of the quadruped robot. Of course, it increases certain problem also, that is it reduces the locomotion speed and increases the posture disturbance. Okay. So best suitable compliance is actually must for a specific type of robot configuration. The objective can be achieved by a simulating model of quadruped with some initial assumptions of link and body parameters. Okay. And simulation can be carried out by varying the stiffness and resistance, and its values can be finalized for maximum locomotion speed and minimum posture disturbance of the robot. Now, the optimum stiffness and load coming on each leg becomes the key parameter for the design of the spring used in the compliant link. Suppose the number of turns of the spring, okay, this can be decided by the popular formula, that is delta G d by 8 W C cube, where delta is the axial deflection derived from the load versus by stiffness, G is the modulus of rigidity of the spring material, D is the wire diameter, and C is the spring index derived from the coil diameter to the wire diameter. Okay. And developed robot has commercial available link which is prismatic in nature. So, this is what we procured. It is a internal hydraulic pressure, there is a internal hydraulic pressure providing damping, and spring has been used to produce the compliance here. So, we inserted this one over here to in order to introduce the compliance in the link. Then coming to the kinematic structure of the robot, we assumed actually the knee joint and the two hip joints basically. This hip joint and this knee joint, they are in the sagittal plane, whereas this hip joint is in the vertical plane. Okay. Usually the kinematic structure of a quadruped robot should be simple, and it allows the robot to perform a wide range of tasks. Okay. And here you can see that we provided this hip joint feature actually for additional degrees of freedom, but this was the provision only in the developed robot, that is not there. Now, coming to how the leg should be positions, okay, how the leg should be attached with the body. There are different ways in which the leg may be attached to the body. Okay. If the knee points to the front, as you can see over here, okay, the robot is termed as the forward configuration, and if they point to the back, the robot is termed as the backward configuration. So, this is the backward configuration and this is the forward configuration. Okay. So, we have the four possible configuration. These are the forward, okay. This is the forward, or we have the backward, okay, and this one is forward backward, and then we have the backward forward. Okay. So, here it is reported in the literature that the last configuration, which is the backward forward configuration, is most beneficial one, as it reduces the slippage between the feet and the ground, and it improves the stability of the motion. Then next task was on the selection of the actuator. Okay. So, to select the actuator, we need to do the estimation of the torque, okay, what size of actuator we are going to take. All right. For that what we do, estimation of the torque. Okay. The four legged here we modeled with the bounding gate. Okay. And the four faces, in case of bounding gate, the four faces are basically this is the back in contact with the ground. So, we call it as the back stance, and here both the legs are there in the air. So, this is the flight after back stance, and here this is the front stance, the leg is front leg is in the contact with the ground, and this is the flight after the front stance. Okay. So, here again both the legs are there in the air. Okay. And this is actually the what I was telling you, the sagittal plane model basically, okay, of the four legged robot. So, after as I said, after deciding what configuration we are going to use, okay, as I said, we selected here. Okay. After deciding what configuration we are going to use, actually we can calculate this torque, okay, requirement. So, here is the basic schematic for that. We considered an inclined plane here with say angle theta p, okay, and this is basically you can say that the sagittal plane model. These are the bottom links which are complied, and this one is the rigid link, this one is the rigid link, and this is the body basically, and other parameters are specified over here such as link length, okay, here L1 link length here, okay, and then what the mass of the say bot, okay, and here are the two basically joints for say the rear leg, and here are the two joints for the front leg. Okay. So, all links and body are assumed to be cylinder and uniform, and this why we considered this sagittal plane model, because the derivation of the expressions is simpler. Okay. So, here in this slide all the parameters are defined, basically half of the distance between the hip joints, body of the mass, body mass, body radius of gyration, spring stiffness, damping coefficient, free leg length, 0 spring force, L1 L2 link 1 and length 2 length respectively, M1 M2 mass of link 1 and 2 respectively. Then this is the inclination of the plane, this is the body angle with respect to the inclined plane, and these are the joint angles say of the back leg, theta 1 theta 2 and theta 3 theta 4 are the that of the front leg. Okay. So, the equation of motion for the back stance phase and the front stance phase, why we consider this, because so the torque applied at the back leg, that is in case of link 1. So, this is going to be the torque. You can see there is a huge expression over here involving all the parameters, okay, and the torque applied at the back leg, that is the link 2 is can be evaluated over here like this, okay. So, that is there. Then the torque applied at the front leg, that is the link 1, okay. This tau 3 can be evaluated like this, and torque applied at the front leg, that is of the link 2, this tau 4 can be evaluated. So, what I am saying is that we have evaluated these 4 torques, tau 1, tau 2, tau 3 and tau 4, where the actuators are placed. Okay. So, the torque at each joint is calculated using the equation shown as we have seen previously. Movement starts from the initial position where each joint position is at 0 radian, velocity 0 radian per second, and a acceleration value we have assumed, that is 3 radian per second square, is this value has been assumed, and we have considered that the robot moves on this inclination radial slope, and then we calculated these torques values. So, 5.83 Newton meter, 2.81 Newton meter, 6.38 Newton meter and 8.737 Newton meter for joint 1, 2, 3 and 4, okay, respectively. Now, estimating higher side of torque is a safe part of the design process. So, we considered a certain factor of safety, okay, and we took torque as say 15 Newton meter. Okay. So, the actuation system must there be able to produce this much amount of torque. So, next after the calculation of the torque, the next task was the selection of the actuation system. So, we wanted to make it compact. So, we went with the electrical actuation system, and for that we used the brushless DC motor, most stable for robotic application, as they are have high speed, high torque, high efficiency and low maintenance than other type of motors. And these brushless DC motors have electronically controlled commutation system basically, and because of the absence of brushes, they are faster. As brushes create friction. Also maintenance is less, as no brush need to be replaced periodically. I have talked about this brushless DC motor in my electrical actuation lecture. Now, these brushless DC motors are costlier and their controllers are more complicated. So, that is one problem with them. But looking at the positive side of brushless DC motors made by the Maxon we have used, and this motor unit comprises of basically the motor, the gear head and the encoder, okay. And these units were selected such that we get the required torque. Okay. So, the major specification of the Maxon motor unit which we used in this case, these are the parameter and values. So, we used the brushless electronic commutation 4 pole motor Maxon 1, voltage range 48 volt, no load speed 16,500 rpm, and the no load current is 422 milliampere, nominal speed 15,800 rpm, nominal torque 118 millinewton meter, stall torque is 3430 millinewton meter, and maximum efficiency is 89%. Okay. Then here are the parameter for the encoder. So, encoder again with line driver Maxon we use, the count per turn 1000, number of channels 3, planetary gearhead this GP42C from the Maxon was used, and see the reduction 230 by 1. Okay. So, there is increase of torque 230 times basically, and there are number of stages 4, and the maximum continuous torque is 15 Newton meter. Okay. So, now you can see why we have gone with this gearhead, because as I said here we assumed this 15 Newton meter our requirement. So, based on that we went with this gearhead. So, this was the electrical actuation system for the quadruped robot. The gear, brushless DC motor is here, encoder is here, and this is how the entire assembly is. Okay. So, this is put over here and this is put at the back, and this is how the entire assembly looks like. Okay. Then next job was on the selection of the controller. Okay. So, the controllers are the brain of the entire quadruped system, and to maintain the better compatibility with the actuation system we went with the Maxon controller only. Okay. And for the position control, a discrete PID controller with anti wind up acceleration feed forward and velocity feed forward can be implemented using a DSP, that is the digital signal processor, where the sample time can be taken as 1 millisecond, much smaller than the mechanical time constant of the typical drive system. And as per the Maxon recommendation, compatible controller for selected drive is EPOS2 P24/5, which is freely programmable position controller which we used over here. So, the major specification of the Maxon controller units are these basically. So, this is the controller which we used. This is the operating voltage 11 to 24 volt DC. There were 6 digital input channel, 2 analog input channel and 4 digital output channel, and interface is with the help of RS-232 ports, CAN and as well as USB 2.0. To control 8 motor units, because we used 8 motors, okay, the 2 in the each leg. Alright, so to control each motor unit one need 8 controllers. Okay. So, there is one master and 7 controllers. So, out of these 8 controllers one can be treated as or converted as the master controller, and other 7 can be treated as the slave controller. Each controller controls one motor unit, and the master controller does position control of its own motor as well as send signal to the other slave controller. Okay. That way it controls the other 7, send signal to the other 7 slave controller. Now, other characteristic of master controller, that is EPOS2P or IEC 611313 programmable, can open master function, multiple axis system via CAN bus, CAN open, point to point control unit and interpolated position mode. So, this is the structure basically, the controller connection with motor, which you can see we had a PC, there is a USB or RS-232 port for the communication, we have the master controller, okay, and there are 7 slave controller connected to CAN open slave network, CAN-S, okay, and here are the drives. Okay. So, this master controller controls its own motor, and this sends signal to the other 7 slave controller, and these slave controller in turn control these 7 other motors. So, this is the controller connection with the motor which we used. So, EPOS Studio was used for the programming purpose. Okay. Many decentralized control can be easily managed with complex program in EPOS Studio. Desired input data are given in terms of the encoder increment, which is called quad count, and entire process of locomotion, planning and execution are presented in the flow chart. Okay. So, this is how we planned and executed the motion planning for that. Okay. So, we start and then we move to the what type of gate we are going, our robot is going to follow. Then the determination of each joint position with respect to time, okay, and the conversion of each joint desired position, velocity and acceleration in form of the quad count. Okay. So, this is done, and then the code in open PCS using MC move relative function block, and then it is sent to the master controller, and the master controller in turn communicates with the slave controller. Okay. And so, master controller also give command to its own motor. So, the control command to the motor is given from the master controller as well as the slave controller over here, and there is a motor feedback that can be given to the master controller as well as slave controller over here, and then reset leg to the initial configuration and operation of leg as per the gate pattern, and then it exit. Now, the sensors. So, we have seen the actuation part, we have seen the controller part. Okay. We have seen the compliant link part. Next, let us look at the sensing part. Okay. So, the information about body's angular and translational motion is obtained by MPU 6050 sensor. Okay. The InvenSense MPU, this one sensor contains a MEMS accelerometer and MEMS gyro in a single chip. It is a very accurate and it contains 16-bit analog to digital conversion hardware for each channel. Okay. Therefore, it captures X, Y, Z channel in the same time, and this sensor is mounted at the top of the robot body, and over and above the 3D motion capture system may also be used to determine the position and velocity of leg tip. Now, next is the fabrication and the final assembly. Okay. So, after finalizing link, actuation system and controller, the CAD model is prepared, and specification of the specification of the developed quadruped robots are following. So, these are the length of the upper link, length of the lower link which is compliant, body length, body width, body thickness, quadruped robot weight approximate it is of 15 kg size, and the main power source is 24 volt DC, and the power supply can give current of the rate of 63 ampere. Okay. So, this is what you are seeing, it is a SolidWorks model basically. So, you have the compliant link over here, and these are the two joints. This is the extra joint which in fact we did not use. So, and these were all actually our the controller which were there, and here you have the actuator, gear head as well as the encoder which is used as the sensor, and this one is the finally prepared model. As you can see, our controllers are placed over this one, and here is the unit for the motor, gear as well as encoder, and this is the prismatic link. Pattern is prepared for hub and upper link, and they are casted from aluminum by sand casting process, and they are machined and final sizing was done. Robot chassis were prepared from aluminum channel. Lower link, as I said, it is a ready made purchased, and then it is modified by introducing a spring to get the compliance, and cabinet is fabricated from the GI seat. So, the results we attempt was made to operate the developed quadruped robot for various gait patterns. We carried out many type of analysis. You can look at the various publications from our group on the various results or the various tests which we carried out. Ample gait, which is statically stable gait, in which legs operate one by one, that is 1 4 2 3 sequence, and here experiment results are shown for the amble gait as I told you initially, and it took 3.3 second to complete one cycle. Okay. So, here is the quadruped robot in the walking position. Basically, we put an indicator over here leg to just show the walking motion over there, and here were the plots. So, leg 1 joint 1, leg 1 joint 2, similarly leg 2 joint 1, leg 2 joint 2, leg 3 joint 1, leg 3 joint 2, leg 4 joint 1 and leg 4 joint 2. So, these were the plot of the legs joint, and if you want to further look into our work and say make a similar type of board, you can refer to our publication in Sadhana, that is development of compliant legged quadruped robot. Thank you.